We're going to run through the basics of how sensors work, and I'm talking the basics because really it's obviously much more complicated. Depends on the sensor. All sensors work in slightly different ways, but at least for the passive sensors, the ones that are recording reflected electromagnetic radiation, they all have some similar components. So they're all going to have some sort of a telescopic system. And this is where the light that's reflected back from the Earth's surface is gathered and it's directed onto a series of mirrors. In this example, there's a scanning mirror that moves back and forth to actually scan from side to side of the image, but they don't all have that. But there is some mirror that's going to help to focus all of this light, and usually is a series of mirrors that focus all of that electromagnetic radiation onto one focus point. And usually at this focus point, the light needs to pass through some sort of a prism or a filter to separate the full spectrum of electromagnetic radiation down into whichever bands the particular detectors are recording. So in this example, the filters are actually located on the shutter wheel. So the detectors are the actual CCDs that record how many photons that have been filtered for a specific wavelength are being received by the sensor. Usually there's also then some sort of an amplifier that takes that electrical impulse, because as the photons are hitting the detector, they're actually stimulating the release of an electron, and typically that's a very low signal, so it'll be amplified before it's then transmitted down to a station at the Earth's surface where the data is actually recorded. Let's look at that in a little more detail. So what we have as an example here is a multispectral scanner. And it has a telescoping system here which focuses the reflected data, the reflected energy from the Earth's surface onto the scanning mirror. And the scanning mirror is really determining where it's looking. That sends the light to a primary mirror, which it then bounces it to a secondary mirror. All of this is focusing that electromagnetic radiation onto the focal point. Here, it's a fiber bundle that has a filter within it that separates all of that radiation into separate wavelengths and sends them to their component detectors or sensors. This data can then be amplified and stored within the system before it's transmitted. So I've expanded this out a little bit to give you an idea of how this sensor is collecting the data. So the mirror, here comes our storage. The mirror is going to concentrate all of that energy on the fiber bundle, but the mirror is also going to scan back and forth so that it's able to focus on different locations on the ground in sort of like a sweeping or a whisk broom. So let's just talk about that for a second. Whisk broom sensors, also referred to as a cross-track scanners, are the ones that are using this mirror, the scanning mirror, that reflects the light back and forth across the image swath. So at any given moment there's an instantaneous field of view where it's essentially seeing one pixel on the ground, but as that mirror scans, the field of view shifts and covers the entire swath. And then as the sensor itself moves, the area it's covered shifts with it, and then the mirror would have to swing back and then scan again. So essentially, this type of sensor is collecting measurements from one pixel at a time before it then scans over to get the next pixel, and so on and so forth. These are pretty common, but the moving parts in this type of sensor make it relatively more expensive and also more likely to wear out. But there are benefits to this type of sensor as well, and one of those is that you only have as many detectors as you would have bands in your image, because the detectors just shift to look at a different pixel to record radiation at a different location. So maintenance is a little bit easier in that there aren't as many detectors that they have to keep calibrated. Also, these are our sensors that have the pointing capability, which gives them higher temporal resolution because they could actually point to see an area that's not directly below them as the satellite passes. But one other problem that has to be incorporated in the pre-processing of this imagery is that as that mirror is scanning, the area on the ground that it's able to see, its instantaneous field of view, is going to be slightly larger when it's looking off nadir, or in other words, off to the side, than when it's looking straight down at nadir. And that's just because it's looking at the ground at an angle, which makes it cover, the same field of view covers a larger spatial area on the ground. So there's additional processing that has to go into making these types of images usable. In contrast, push broom sensors, or they're also referred to as long track scanners, use a much larger line of detectors that are arranged perpendicular to the flight direction of the spacecraft. And so as the spacecraft moves forward, the image is collected simultaneously as one line at a time, with all of the pixels in a line being measured simultaneously. What's nice about this is that the push broom scanners receive a stronger signal than the whisk broom scanners because they look at each pixel for a longer period of time. So in other words, it's not having to scan back and forth and move very quickly from collecting electromagnetic radiation from one pixel to the next. But the drawbacks of this is that it requires much more detectors, and these can have varying calibrations or varying sensitivities. If they're not perfectly calibrated, you can see stripes in the data, and sometimes you'll see that as well if you look at an image and you see artifacts where certain lines are particularly a little bit brighter or darker than the ones adjacent to them. So essentially, what makes these more complicated is that now instead of just having a few detectors for each band you want to measure, they have to still have a few detectors for each band they want to measure, but they have to repeat that across an entire detector array so that they can simultaneously measure the pixels all the way across the scene. So many more detectors are required for this. Also, these can't point off nadir. Their temporal resolution is whatever it is. They have to be flying over an area directly to be able to see anything or record any data. So we've just talked a lot about detectors and how having more detectors can be complicating. And so let's talk about that a little bit more and what detectors actually are and what they're doing. So most sensors have detectors that are built from silicon chips. These are called charge coupled detectors, or CCDs, and they're very light sensitive. So essentially what happens is as photons of light hit these detectors, an electron is excited, which is recorded by the detector, and we thus have a measurement of radiation. But the problem is reflection and photons coming from the surface are not the only source of energy that can excite electrons within our silicon detectors. And it's important to measure this ratio of how much actual electron excitement is happening because of the reflectance and the photons that are hitting that detector versus how much electron excitement, or this electronic signal, is created just because of noise inherent with the instrument. And so every sensor has a way of measuring that for each detector, and it's called the signal to noise ratio. And essentially all that you're doing is you're comparing the level of your desired signal, the actual reflectance you're trying to measure, to the level of background noise. And this is measured actually in a pretty simplistic way by closing the shutter on the sensor so that no reflectance, so that no electromagnetic radiation is actually entering the sensor, and the detectors are just measured to see what they're recording essentially in the dark. This is called a dark calibration. So they can use that to determine how much noise signal there is for a given detector. So obviously we'd like to have this signal to noise ratio be relatively high so that the actual signal that we're trying to detect and measure is much stronger than any background noise that might be just introducing random signal. And sensors are very carefully developed, and detectors are carefully developed to improve this signal to noise ratio, because essentially the quality of your image is determined by that signal to noise ratio. So the performance and how well you're actually able to see or distinguish features is really dependent upon how strong that actual signal is you're trying to measure versus how much background noise there is. The more background noise there is, the more washed out your true signal will be. So if you had a very high signal to noise ratio, you would expect that you'd be able to see the true reflectance coming back from your object of interest much more clearly without having all of that background noise included. So where is all of that noise coming from? There's really two primary sources within the instrument itself. One we refer to as dark noise, which is essentially how much the electrons within that silicon detector are being excited just by the heat generated by the instrument itself. And I know this is counterintuitive because we actually have temperature decreasing here on the x-axis. So here are the warmer temperatures. But you can see how much the electrons are actually excited based on the temperature, and it really is a sort of intrinsic curve where the warmer it is, the more noise you're going to have inherently. And that's why many detectors, especially those that are recording radiation from longer wavelengths, which inherently have a lower signal noise because they have less energy associated with them, will actually have to have a cooling device installed around the detectors to minimize that noise so that they can still actually see the true signal. There's also some noise that just comes from the system components that are trying to convert that electron charge into a voltage signal that then in turn is actually recorded as a measurement to quantify how much radiation is hitting that detector. And this is typically pretty constant across all of the detectors, and so there's a nice fix for that in the pre-processing. So this should hopefully give you an idea that before we even download our imagery, before we do what we call pre-processing in converting to reflectance or doing an atmospheric correction, there's a lot of pre-processing that actually goes on in-house before we even see any of those images to remove a lot of these different noise components and maximize the signal. So we've talked about the parts of a satellite sensor system and essentially how they're collecting and recording data and the different ways that they might be scanning the Earth's surface to be able to receive that data. But we also have to talk about how satellites actually orbit the Earth. And there are two primary types of satellite orbits. One is called a geostationary orbit, also referred to as a Clark orbit, and the other is a sun-synchronous orbit. So we're going to go into YouTube, where I think that someone with better artistic skills than I can explain each of these. And we'll start with a geosynchronous orbit. Be ready to adjust your volume here. I'm not sure how this is going to transfer from me talking to my computer.
Geo means Earth, and sync basically means the same, like if two people are in sync, they're thinking the same way or doing the same thing. And chronos, that comes from the Greek word for time. So think Earth, same, time. And here's the idea. Imagine standing and spinning something around your head. So you've got a rope and there's a rock on the end and you're twirling it around. And you've no doubt done something like this before. You spin something around. And you know that if the rope is really short, it spins around and around really fast. And if the rope is really long, it goes around more slowly. Well, planetary orbits or orbits of something going around a planet move in a similar fashion. So if you have the Earth here, something going around the Earth will orbit relatively quickly if it's close to the Earth, and something very far away will take a long time. For example, the space shuttle orbits in low Earth orbit, just barely out of the atmosphere, just a couple of 100 miles above the surface. And the space shuttle goes around the Earth about once every hour and a half. So it's about 90 minutes for an orbit. If you go way out, the moon is about 250,000 miles away, and the moon's orbit takes about 1 month. So the farther things are away, the longer it takes to orbit, and the closer they are, the shorter time it takes to orbit. Now, there's a distance in here in between these two, in between the low Earth orbit of the space shuttle and the 1 month orbit of the moon. There's a distance in here at which an object will make exactly 1 orbit per day. Okay, and this orbit once in 24 hours. And an object orbiting once every 24 hours is said to be in a geosynchronous orbit. And here's why. If you picture the Earth here, and let's picture the equator like this, and so the poles of the Earth, you can imagine the Earth's axis running through there. And so the Earth is rotating on its axis. So let's imagine it's spinning this way. It's spinning around, and now let's imagine an object in orbit. And here's the orbit out here. So the orbit goes around the Earth, kind of seen in a perspective view, something like that. Now let's imagine that it's at just the right distance away so that it makes one orbit per day. Well, this object goes around in its orbit once per day. The Earth also goes around once per day. So let's imagine that the object is right here, and you're standing on the Earth right there. Well, as this object goes around once per day, you also go around once per day. So relative to you, the satellite that's orbiting the Earth, it doesn't appear to change position in the sky, because as it rotates, you rotate. And if it rotates through 30 degrees of angle, you also rotate through 30 degrees of angle. If you are both making one lap per day, you're both rotating at the same angular speed, the same number of degrees per hour. So the result is an object like that, if it's in an equatorial orbit, an orbit where the plane of the orbit is the same as the plane of the equator, then that object will stay right over the same location on the Earth all the time. And that's a good thing. That's where they put communications satellites, like a satellite for dish TV or something like that, or any kind of satellite that's beaming a signal regularly down to Earth. You want to be able to set up an antenna and aim it at the satellite to pick up the signal. And you don't want to have the antenna tracking the satellite all the time. That satellite will stay in the same point in the sky the entire time, all day and all night, if it's in a geosynchronous orbit, because as it moves in its orbit, the Earth is also rotating, and it stays exactly over the same point all the time.
One interesting fact to impress your roommates with tonight is that actually these geosynchronous satellites don't orbit in 24 hours. They actually orbit in 23 hours, 56 minutes, and 4 seconds, because that's actually how long it takes the Earth to rotate once about its polar axis. The 24-hour period comes in relative to the sun, in terms of that orbit relative to the sun and when we would see the sunrise on a given day. So I feel like he gave a lot of reasons for why geostationary orbits are good. They do see the exact same location on the ground all the time. So there is a basically continuous revisit time, so infinite temporal resolution. But there are some downsides to this orbit, and one of those is that in order to match the rotation of the Earth, they have to be at approximately 36,000 kilometers above the Earth. This is pretty high. This is a pretty high orbit, which gives them a lower spatial resolution. So thinking back to our different resolution terms, what we're saying is that because their orbit is so high, their pixel size is really large, so they're not able to see fine detail on the Earth's surface. But that's okay, because typically these are used for much larger scale phenomenon, such as hurricanes, a lot of weather patterns, or just communications, where you always want them to be visible to a very large area anyway, and having fine spatial resolution isn't that important. The other disadvantage is that they often have trouble monitoring anything near the poles, so where they can see very easily the equator and roughly see half of the globe at any given time, their coverage at the poles is much weaker, making those areas harder to study. Most of our Earth observation applications, though, have satellites that are in something called a sun-synchronous or a polar orbit. And what this does is it ensures that as satellites rotate the Earth over the poles, that they're able to record imagery of a given location at the same time each day. So this helps to ensure consistent lighting conditions at the least, or as consistent as possible, not counting seasons, so that we can have some way to measure or compare over time. So again, just to try to demonstrate how this is working with an orbit that continuously passes over the poles, and it's orbiting really in the exact same location, but it's the Earth that's rotating underneath of it that allows it to cover larger areas of the Earth. And this is kind of hard to visualize, so again we're going to switch over to YouTube and see how Ian Woodhouse can do.
So here's a video actually showing you the coverage of the measurements of this satellite. This just happens to be the Aqua satellite. It's another short video here from NASA, and it's showing you that sort of purpley blue band beneath the satellite. is the width of the measurements that the satellite is taking. So you can see the little green lines are the scan lines of the measurements that it's taking. It doesn't matter if it's taking measurements of the atmosphere or the Earth's surface here. It just gives you an idea of the coverage of the measurements. This is quite a wide swath of measurements. So the width of this path, this swath, is actually so wide that when the satellite comes around for a second time, it actually overlaps with the first pass. Now, if it takes about 90 minutes for a satellite to orbit the Earth, then you can see that maybe a dozen times, so about a day or not much more than a day, you're going to have full coverage of the Earth in this particular orbit. The orbit goes up and over the poles, and it comes down around the equator, and so it covers all parts of the Earth because of the overlapping swath. Now, not all satellites are like that, and clearly the width of the measurement swath, so the range of the geometry of the measurements has an impact on how much area is covered, but also the satellite flying altitude has an influence on how much that apparent coverage is on the Earth's surface. Here's another satellite with a slightly narrower swath. It's actually the same satellite, still Aqua, but it's a different instrument, and it's now scanning over a smaller area on the Earth's surface. So you'll notice that when it comes around for the second orbit, at the poles it actually crosses over, but as you reach the equator, there's actually a gap in the coverage there. And clearly, if you went to a satellite with an even narrower swath, the gap in the coverage would get larger, and it would therefore take many more orbits to get around the planet in order to get full coverage. Some satellites, in fact, have such narrow swaths that it can take a whole month before the entire surface of the Earth is covered using this kind of polar orbit. You'll also notice that because the Earth is rotating underneath the orbit, so the satellite is going round in its orbital plane, and the Earth is turning underneath it, that it means that the polar regions actually get covered very well. There's lots of measurements at the poles, and the equatorial regions are the ones most likely to have the gaps. So getting full coverage at equatorial regions from this kind of orbit is harder to do than in the polar regions.
So hopefully that made more sense. But just to summarize, the reason why we need to understand what our orbit type is because just like with our different resolutions, there are trade-offs. And so the choice of orbit, which orbit, whether you're sun synchronous or geosynchronous, and which altitude you're at if you're sun synchronous, are really going to influence how often you can receive measurements of each given spot on the Earth, so your temporal resolution. It also determines how much surface area you cover with a given swath. It determines the resolution of your sensor, the spatial resolution of your sensor, and then other things just like data download. So for example, these satellites are collecting data continuously, but the sun synchronous orbits, they only pass over the stations that can receive the transmissions of this data at certain intervals. And so if you want to be able to download data in near real time, you would need to have an orbit that could cover a larger swath of the Earth and therefore be in contact with more data receiving stations. Also, the cost of the launch is something to think about. Those higher Earth orbits are much more expensive to launch. So there are a lot of trade-offs that go into the decision of what type of orbit a given sensor should be launched into. So let's wrap this up now and assume that you understand the basics of sensors, how they work, how they collect data, and how they orbit the Earth. And we'll end with something just a little more fun, thinking about how many man-made satellites there actually are currently orbiting the Earth.